All right, y'all. So this is our first video in our chemical bonding series. So there's a couple of different concepts that we're looking at in chemical bonding. And the first thing that we're going to talk about is extension of electron theory from the last thing y'all probably ever learned about it, which was Bohr models. All right. The Bohr model is a really great way to show all the parts of the atom, the nucleus, the protons, neutrons, and the electrons, and especially the valence shell. But it is inaccurate in that the Bohr model makes it look as if electrons are in these specific fixed orbits, which means that you should be able to pinpoint the location of an electron at any point in time, which is actually not true. There is a principle called the Heisenberg uncertainty principle that says it is impossible to know both the momentum and the position of a particle, meaning an electron, with any certainty. So in 1926, a man named Erwin Schrödinger, who was a mathematician, used some advanced mathematics to instead describe the position of electrons as a 3D area where it is most likely going to be occupied. So we can't really say the electron is going to be here. We can say it's going to be somewhere in this area. And that's where we get the electron cloud model, which is the current accepted model of the atom. So we still consider that electrons exist in certain energy levels, and then there are certain quantum numbers that are assigned to each electron to describe its properties. So those quantum numbers relate to different parts of the electron configuration of the electron. The first one is the principal quantum number, which is the energy level that the electron is going to exist in. And for the most part, it's going to match the period that the element sits in. The second one is the angular momentum quantum number, which is a fancy way of saying the shape of the orbital. There are four shapes, S, P, D, and F. And each one, as you go from S to P to D to F, you are increasing the energy of the electron. And then the last one that we're going to be interested in right now is the spin quantum number, which is either plus a half or minus a half, which says that the electron is rotating either clockwise on its axis or counterclockwise. And so here's an example of the shape of the S, P, and D orbitals. So S orbitals are spheres, and they can hold up to 2 electrons. P orbitals are dumbbell-shaped, and there are 3 suborbital designations for P, depending on which axis it's sitting on. So there's the X, the Y, and the Z axis. And so each suborbital can hold 2. So a p orbital can hold a maximum of 6 electrons. And then d orbitals, there are 5 sublevels. Each can hold 2 electrons that spin in opposite directions. So a d orbital can hold up to 10 electrons. And then the f orbital has a really weird shape, but there are 7 sublevels to f orbital, and so therefore they can hold up to 14 electrons. So when we write an electron configuration, what we're doing is showing the location of all of the electrons in the element in their respective orbitals. And the rule is that elements like to assume the arrangement that has the lowest possible energy, which is called ground state configuration. So we talked about that in the last unit when we talked about the emission spectra that Bohr used to base his model off of. So a electron in the first energy level has a lot less energy than something in the 7th, and then the s orbital is the lowest energy level, or lowest orbital in that energy level, and then f would be the highest for the ones that have an f orbital. So all energy level designations have an s orbital. P orbital shows up in the 2nd energy level. D orbitals don't show up until the 3rd, and f orbitals don't show up until the 4th. And then only the 4th and 5th energy levels have an f orbital. Now, there are three laws that govern electron configuration. The first is the Aufbau principle that says an electron will go into the lowest energy orbital that can receive it. So what that means is you have to fill the 1s orbital with 2 electrons before you can start occupying electrons in the 2s orbital. The second is the Pauli Exclusion principle that says that no 2 electrons have the exact same set of quantum numbers. And for the most part, we just use that to note that if you have 2 electrons in the same orbitals, like the 2 that are in 1s, one spinning clockwise, one spinning counterclockwise, so their spin quantum number is different. And then the last one is Hund's rule, and that says that if you have electrons that are filling into orbitals that are equal energy, each equal energy orbital has 1 electron in it before anyone has 2. So that has to do with the sublevels of P, D, and F. So each of the 3 P sublevels will have an electron in it, and then they will fill 2 into each before the P orbital is full. And so on and so forth. So it's also kind of like, we call this the seats on the bus rule. So if you're getting on a bus and you don't know people, and then there's an empty seat, you're more likely to sit in the empty seat than you are to sit next to somebody you don't know. And so we have the orbital blocks on the periodic table, which we kind of looked at with the Engage assignment that we did. So groups 1 and 2 are the S block. So that means if the element is in group 1 and 2, then its last electron is filling into an s orbital. And remember, for this concept, helium is over here next to hydrogen in s block. P block is groups 13 through 18. So if it's a group 13 through 18 element, its last electron fills into a p orbital. D block is the transition metals. And so if it's a transition metal, its last electron is going to fill into D block. Now, when we're doing the electron configurations, remember the d orbital designation shows up in the 3rd energy level, but you actually don't start filling it until after you've filled 4s, because 4s is slightly lower energy than 3d. So that's what this n-1 means. It's that the number in front of the d for this orbital designation is going to be 1 less than the period the element is in. And then the lanthanide and actinide series is where you're going to see f orbitals start to come into play. And remember, lanthanide and actinide show up in periods 6 and 7, respectively. But the first f orbital is in the 4th energy level. So with the lanthanide and actinide series, the number in front of the F for that designation is 2 less than the period that the element would normally appear in. So most people find it easier to just know this order of fill diagram. So if you write out all of the possible orbitals that I've written out here, and then you draw arrows diagonally across, then it will show you the order that the elements will fill in their electrons. So we start with 1s, and then we follow the arrows around and down. So after 1s is 2s. After 2s would be 2p, and then 3s, and so on and so forth. And then if you remember that each principal energy level can hold 2n squared number of electrons total, so like the first energy level can only hold 2, the second energy level can only hold 8, and so on and so forth. And as long as you remember the maximum number of electrons each orbital letter can hold, you will be able to use this very easily to do an electron configuration. Sometimes we can also show electron configurations with what's called orbital notation, and that is where you draw a line and write the orbital name underneath, so the principal number and the letter, and then you use arrows to show the electrons. And so with the Pauli exclusion principle, when we're filling in electrons to the same orbital, if we've got 2 occupying the same orbital, the arrows are drawn opposite each other to indicate opposite spins. So this is how we would do the orbital notation for hydrogen, and then this would be how you would do helium. So hydrogen only has the one electron, and it will fill into 1s. So we just draw one arrow in the 1s, and then helium has two, so we'd be one arrow up, one arrow down to show opposite spins. So the normal electron configuration of the element is called its ground state configuration, and that's where it's the most stable. But as we've seen in the last unit, if an electron absorbs enough energy, it can be forced into a higher energy orbital where it would normally not be, and we call that excited state. And so you can tell an electron is in an excited state when it's in a place where it wouldn't normally be. So for example, if I saw this electron configuration, this 2p orbital is not full, but this has got an electron in 3s. That indicates that an electron has been excited out of the 2p orbital and into 3s. And since if I add up these superscripts of the electrons, that is the total number of electrons configured, and it's also the atomic number of the element because we're assuming the elements are neutral. Then 2 and 2 is 4, and 3 and 7, and 1 is 8 would tell me that this would be an excited oxygen atom. So to write your electron configuration, first you're going to figure out how many electrons you have to configure. And then you're going to use the order of fill diagram starting with 1s, and you are going to add electrons into each energy orbital until it's filled, and then you move to the next one. So, for example, with hydrogen, it only has one electron. You have to start filling with 1s. So the electron configuration of hydrogen is 1s1. So this tells me the orbital, and this tells me how many electrons are in it. So in another example, nitrogen has 7 electrons. So again, we are going to start with the 1s. So 1s, s can hold up to 2, so 1s2. After 1s, if we look at the order of fill, is 2s. So 2s and then 2 to fill it. And that gives me 4 electrons filled there. So we have 3 more to configure. After 2s, if we follow it around, is 2p. And so we only have 3 electrons left to configure. P can hold up to 6. So the last 3 electrons in the nitrogen element will go into the 2p orbital together. So the total configuration of nitrogen would be 1s2, 2s2, 2p3. And you can check to make sure you did it right, because if you add up the superscripts, it should add up to the number of electrons that you configure, which is also the atomic number of the element. So as you can probably tell, as you get down into the transition metals in the lanthanide and actinide series, you end up with these very, very long configurations. And that can be cumbersome to write. So an acceptable alternative to writing out the whole electron configuration is to use what's called noble gas notation. And so what that is you find the part of the configuration that matches the noble gas nearest to that element. And you can tell because noble gases always end with the designation 2p6. So what you do is you take the whole part of the configuration that includes that 2p6 designation and substitute the symbol of the noble gas that represents in brackets, and then you just write the rest of it. So if we use silicon as an example, the long form of silicon's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p2. All the way up to 2p6, this half of the configuration is neon's configuration. So I could take all of this, the 1s, 2s, and 2p, and substitute neon symbol in place of it to represent the core. And then what's left is what is not the core. This is the outer level. So another acceptable way to write the configuration for silicon would be neon in brackets and then 3s2, 3p2. You can only do this for the part of the configuration that represents a noble gas. All right. Now, the electrons in that highest main energy level in the s and p orbitals specifically are the valence electrons that participate in bonding. So if I look at an electron configuration and I look at the highest energy s and p and add their superscripts together, I can quickly determine the number of valence electrons in the element. So for this example in nitrogen, this 2 in the 2s and this 3 in the 2p are nitrogen's valence. 2 and 3 is 5, and I can verify that by looking at the periodic table. Nitrogen is in group 15. It has 5 valence electrons. The ones that are not in the valence are called inner shell electrons. We can also use an element's electron configuration to figure out what element it is. And there's a couple different ways you can do this. You could look at the last part of the configuration, and this is like the element's address. So if I look at this, the principal number tells me what period it's in. The letter tells me what block of the periodic table it's in, and then the superscript tells me how far into that block it's in. So if I look at this configuration, 3p5 says I'm looking at the element in the third period in p block in the 5th place, which would be chlorine. Alternately, you could just add up the superscripts for all of the configuration, and that will match the atomic number of the element. So this is an example of doing that, using the same configuration. And again, this is for neutral atoms, so it has to be specified that it is a neutral atom. If they don't specify, otherwise you assume that it's a neutral atom. Now, we've kind of talked about ions in the past, but we haven't looked at them real hard. Ions are elements that have gained or lost electrons so that they are like their nearest noble gas. All right, so we talked in the last unit about how metals want to lose their valence electrons and nonmetals want to gain electrons, and they're both trying to satisfy octet rule. All right, so any ion will have the same electron configuration as the noble gas nearest it. So for example, if I was to write the electron configuration of a sodium cation, which is a positive ion, so sodium usually has 11 electrons, but this plus means it's lost 1. So then I would only have 10 electrons to configure, and using the order of fill, that would be 1s2, 2s2, 2p6, and that's neon's configuration. Chlorine usually has 17 electrons, but the negative charge on the chloride ion says it added 1 electron. So now it has 18 to configure, and when I run that through the order of fill, I get the same configuration as argon. So ions will always have the same configuration as their nearest noble gas. Another way that we symbolize electrons in elements is what's called the Lewis valence electron dot diagram. So you've learned in the past that valence electrons are the ones that are responsible for bonding. And so a lot of the time when we're looking at behavior of elements, especially in regards to bonding and reactivity, we just care about the valence electrons. So what we do with this Lewis dot diagram is we use the element symbol to represent all of the core electrons, so all of the non-valence ones. And then we draw dots around the element symbol to show the valence. So when we draw these symbols, the rule is that the valence electrons are going to surround the symbol in pairs, and each side can hold 1 pair for a total of 8 valence electrons, so octet rule. The first 4 electrons go on an empty side of the symbol, and then the last 4 will pair up. And so that also kind of goes with Hund's rule, where you have to fill 1 electron into each orbital of equal energy before anyone has 2. So backing up 1, this is why when we draw the symbol for the electron dot symbol for carbon, carbon has 4 valence, we have 1 dot on each side instead of 2 and 2. So since elements in the same group for the representative elements have the same number of valence electrons, it is reasonable to assume that they will have the same Lewis structure. So all group 1 elements will have a Lewis structure with 1 valence electron on one side of the element. Group 2 will have 2. Group 13 will have 3. Group 14 will have 4, and so on and so forth in this fashion. Now, it is important to note that because the valence electrons are the s and p electrons, and since transition metals, technically their last electrons fill into a d orbital, we don't typically use Lewis dot structures to represent the valence electrons of transition metals. And it is also interesting to note that with the transition metals, they can move their valence electrons around in and out of their d orbital to hide them or use them as they see fit for bonding, which is why transition metals can have multiple ionic states. So they're playing around with their d orbital to do what they need to do. So when we're doing a Lewis diagram for an ion, there's two different ways to do it depending on whether you're diagramming a cation or an anion. With a cation, they have lost all their valence electrons. They have gotten rid of them so that they're back to their noble gas core and they're charged. So all we show for a cation is the symbol of the element in brackets with the charge of the element outside the bracket. So if it's just a plus, that means +1. Calcium, which is in group 2, would lose 2 valence and become a +2 ion. So this would be the ionic symbol for calcium, and so on and so forth. Nonmetals are going to gain electrons to fill their octet and become an anion. Anions are negatively charged. And so to show the Lewis symbol of an anion, you would draw the normal Lewis dot diagram of that element, and then you would draw in the number of electrons they gained to fill octet. So the normal valence are dots and the gained ones are x's. Put that in brackets and put the charge outside of the brackets just like you do for cations. So for sulfur, it would look like this. So sulfur is going to gain 2 to go with the 6 it already has to fill octet, and it's a -2 ion because it had to pick up 2 electrons. And so that is the first part of chemical bonding. In the next video, we're going to talk about how cations and anions combine to make ionic compounds and how nonmetals can share electrons to make covalent bonds.